Hello everyone. Now I will present you a software that is called Romie, and which is a domain-independent tool for computer-aided robust operations management. So first a few words about the context. The idea is to solve the problem of human operations or project scheduling under uncertainty, which involves a number of questions. Is there a gain of using a probabilistic model? That is robust scheduling useful in practice? Another question is, can the work of modeling the scheduling problem be made accessible to the end user? Can we make it user-friendly? Or you must definitely have a PhD or to be an expert in operations research to understand how to model operation or project scheduling problem. Finally, is domain independency possible? That is with a unique model formalism. The paper is organized around those three proofs of concept. So in 2018, there were the Thomas mission. That was the very first proof of concept of the scheduling under uncertainty technology. Then in 2020, we had a collaboration with a Belgian biotech company in order to model and solve problem around biomanufacturing in their company. And finally, in 2021, we considered the problem of scheduling the set of configuration and setup operation in the context of the DARPA Subterranean Challenge for the Jet Propulsion Lab team in this contest. First of all, the Thomas mission, which took place in the Mars Society's desert research station in the desert of Utah. So basically we were a team of 8 analog astronauts, and the idea was to make science in place and to simulate how you make science in such a research station. So everyone came with a research project from many different fields, because we were researchers from many different fields, ranging from chemistry to particle physics or biology, botanics, engineering, medicine, drugs, and so on, and including mine, which was of course operation scheduling under uncertainty. And actually my research project aimed at considering and modeling each and every research project of the other guys in the group. So for instance, here you have models of 2 research projects here. So I took all the different research projects and put it in the same bucket, because of course those problems looks quite independent, but in fact they are not independent because of the shared resources in the research station. So for instance, when one needs to make an EVA for one of the activity of its research project, then other members of the crew must be available to make the EVA and so on. Or if someone using one of the science machine, the science machine is not available for the other experiments and so on. So there are shared resources that makes those little problem actually part of one unique big problem. Then at the beginning, before the beginning of the operation, we solved this problem to compute the provisional planning that includes the 13 days of the mission. And then typically during the operation, so that there we were before the first day of operation, but then start the operations, and I was typically working around people and recording everything that happens. That is, when does that task actually start and when it did ended, being completed and so on, in order to keep the modeling of each problem, the model of each problem, up to date with respect to what actually happened. And at the end of the day, with the updated models, we would simply re-optimize for the next days according to what really happened. The results we obtained from this proof of concept were quite interesting, since we saw that the solution computed based on a probabilistic model were in average 3 times more robust, that is, had 3 times more probability of success than the solution, that is, the plannings you could obtain when optimizing under a classical deterministic model. Here, for instance, we see that the solution obtained with the probabilistic model were measured at around 95% chances of success, whereas the deterministic ones, that is, those being near optimal but under the deterministic assumptions, were of only 34%. And the other interesting fact is the average price of this robustness. And here we saw that in average, the solution from the stochastic model, the probabilistic model, were in average of only 7% more expensive than the solution obtained from the deterministic model. That is, by sacrificing 7% of your cost or your scientific outcome, you could obtain solutions that are 3 times more robust, more reliable. So in fact, there is a gain of using a probabilistic model. And we saw also here with the Belgian biotech company that it was possible, and it is possible, for the end user to understand how to model a scheduling problem and to be able to do it by himself. And that's because that's exactly what we did with the company's head of operations. And this is an example of how we can model the entire production campaign of one of their main products. And here you can see solution obtained when you consider not only one production campaign but 3 production campaigns in parallel. And you can see how the manufacturing campaigns overlap. And again, we saw that we could obtain really better solutions when using the probabilistic model. So roughly, in practice, considering 3 campaigns in parallel, then the success probability of the schedules obtained can be increased from 14% to at least 97%. Also, we saw that in average, the number of extra hours needed to save the schedule when unexpected things happened can be lowered from more than 20 hours in average above the 3 campaigns to less than 9 hours. And finally, here the price of robustness was measured of being about 13%. So not only there is a gain of using a probabilistic model here, but we saw that within only a few meetings, a few hours with the end user, the modeling phase, the modeling process can be made accessible to him or to her. You don't need to have a PhD to be able to rigorously model a scheduling problem. And finally, we saw that domain interdependency is perhaps possible, or at least here we considered a third application case, which is really different from the first ones, since here we have the DARPA Subterranean Challenge, and we used the brand new integrated modeling interface to model the problem at stake here. And there is one last question about astronaut self-scheduling, and I'm actually here launching a call to action by referring to this paper here. I mean, this paper aimed at assessing the capability of astronauts to self-schedule, to self-manage their time and their activity. But so it was a very, very interesting paper, and this is a question that has raised a lot of interest for the future, because astronauts are going to be more autonomous. But here the limitation was that the scheduling tool provided was quite limited, only visualization and edition by hand. So there were no model edition. I mean, you could not modify the problem by itself, and furthermore, you could simply not re-optimize. So I would like to find an application case in which we could assess the capability of the astronaut to self-manage or adapt their operations, for instance, according to unplanned external events, by using our schedule modeling and scheduling tool, in order to be able to re-optimize and for instance making opportunistic science without messing everything up, and to also keep their key performance indicator the higher possible. So feel free to contact me in case you would be interested. Thank you very much.